Hello everybody, good morning. My name is Ghazi Wakili. I'm coming from Switzerland. I have my private company in building physics. Originally I was not supposed to have my presentation at this prominent general session, and I thank the organization to give me this opportunity, this privileged opportunity to speak to the general session. So what I'm presenting is about a hybrid behavior of external rendering and internal insulation in historic timber-framed walls. Well, using historic buildings means also saving them. So when we use the historic buildings, the possibility and the statistics shows that we also save them. If we don't use them, the probability that we will forget them and they will deteriorate is higher. So there's a need for refurbishment. And people who will want to live or have to live in historic buildings, they want to have also the thermal comfort inside their buildings. And this thermal comfort is always becoming more complex with the years. So the requirements of 50 years ago are not as severe as the requirements of today. So there have to be some refurbishment, some changes into these historic buildings. Most of these historic buildings might be under protection so that their external appearance might not be changed or not allowed to change. So the only remaining possibility of changing anything into the thermal behavior, into the energy consumption, or even the comfort of the inhabitants is by using internal insulation. When we take internal insulations, what happens, the first thing that pops into the eye is the external walls are isolated from the room side. So the external walls are becoming cold. These colder external temperatures will be more emphasized during winter time. This would mean that moisture is accumulated in colder layers, and as they are colder, the drying, after driving rain events is becoming reduced. So we have to be very careful with the envelope of the building when we are installing internal insulation. So, there are two possibilities of moisture transport into the building. One is from the room side. This can be altered by using vapor retarders or barriers. And then there is a moisture storage and the moisture storage capability of the insulation. And then there is the moisture transport from outside, especially from rain, if exposed to driving rain. Then the water uptake of the external rendering will be a very an essential parameter which will affect this kind of water uptake and moisture transport, and at the end the moisture content of the cold external envelope. So the question is, how much insulation is allowed to use in these buildings? How much is affordable before something happens which would destroy or deteriorate our buildings? For this, there is a transient hydrothermal simulation which is needed. That means a simulation which takes into account heat and moisture transfers at the same time, simultaneously. So the well-known and, yes, very widespread Glaser method is not applicable anymore. And then the water uptake has to be measured in situ. That means we have to see how can we measure the value of the water uptake of the external rendering. Laboratory values will not consider aging. So if we are making some samples for laboratory measurements of some constructions or renders, this will not represent the reality, the aging, the outwashing of the render during decades. So, we had here the opportunity of having a building, which is a timber-framed historic building near the Lake of Zurich in Switzerland. You see here on the left side, and on the right side, some timber structures in red still visible. But in the center, there is the western facade, which was completely covered with a render. And the question was, what happens on this western facade if you are going to apply internal insulation? We have to know how much water is going to be uptaken by the external render. And the western side is the weathering side. That means the side which has driving rain. This is really exposed to driving rain. The others one have some shelter, but this one is really totally exposed. Just with the exception of the upper parts, which are just beneath the wooden frame. So, here we applied the so-called Franke plates. These are small plates which you have to fasten on you apply them to the wall with a rubber around it, and you fill in water, and you measure during time how much water has been absorbed. And you see on this small part, it has some marks on it, and you can find out how much water is taken up in a certain time. And this is how you have to measure the water uptake in situ of this render. On the right side, you see there is water leaking. So this measurement has to be done a second time. This is a leaking one. It's not good, so you have to take everything out and repeat that measurement. The coefficient of water uptake, this is the formula. It has to do with the measuring surface, which in our case has this value, and the time measuring, we chose 15 minutes, which is 0.25 hours, and the measured weight of water in kilogram. And so if you put these values, you approximately come to a value that the coefficient of water uptake is something like 100 times the measured weight of kilogram, the measured weight of water in kilogram, which I showed you how you measure. So, we had averages of 3 measurements, and we found out that the upper part and the lower part did not have the same water uptake. There is a difference in the water uptake. So we found out that these renderings were done at different times, and just as a final layer was put on it to make it white, but beneath it was different. That's why we have some different values. And then we made a hydrothermal simulation with using climatic data for Zurich, weather side west, just one-dimensional, and we put an insulation material, which is 10 centimeters of mineral foam, and we started to do these simulations. And this is the results. We look at the most important thing is the temperature between the internal insulation and the wall. That means the cold side of the internal insulation. This is very critical. And you see that the temperature beneath the internal insulation layer is above the corresponding dew point temperature. That means you will not have any condensation beneath the insulation layer. This is this case 1 with this lower water uptake and the U value of 0.33 for this construction. We went to the next case, and this is just when we use the higher level. Here again, the temperature beneath the internal insulation layer is above the corresponding dew point temperature. And then, as a third case, we took a very ideal case where the water uptake of external rendering was diminished by a factor of 10. And of course here too, the temperature beneath the internal insulation layer was above the corresponding dew point. So for all these three cases, nothing happens beneath the insulation layer. Now we go to the external side. We look first to the total water content. To the total water content, this is over a calculation period of 5 years. We start with a rather lower content, you see on the left side, and then it comes after 5 years to some, a quasi-static situation. But you have peaks where we reach 20 kilogram of water per square meter of construction. We have high peaks, and these peaks are mainly during the cold season. If we go to the second one, where the water uptake was higher, again there you have slightly higher values, but when we reduce the external uptake, of course, the total water content reduces to half the value. It's only by 11 kilograms per square meter. That means applying, having an external render which has a far lower water uptake coefficient will reduce very much the water uptake of this part of the envelope which is cold during the winter time. We looked also to the temperature and the relative humidity in the rendering itself. I have made here just taken apart and zoomed up to show you what happens really in the render. And this is now just shown for 1 year. It's not 5 years, because 5 years is just repeating itself. I took the last year, the 5th year, where everything has come into equilibrium, a quasi-equilibrium. And you see here that on the right side, on the top, in green you have this relative humidity, and in red you have the temperature. And at very low temperatures, you reach relative humidities of approximately 98 to 100%. That means there is a high possibility that there you will have liquid water, and liquid water at temperatures which are going to 0 and beneath 0 might occur in formation of ice and cracking of the rendering. This does not happen when we have the case 3, where we reduce the water uptake of the external render. Here again, on the right side, on the top, you see the green lines. These are now reaching just under peaks 90% of relative humidity. So we have a reduction of approximately 10 to 15% relative humidity at the low temperatures in wintertime. This is the building itself from inside, the view from inside, that was during refurbishment. We know that there are also timber used there. We made some measurements in the timber to see how the situation and how the status of the timber used in these buildings look like. This is a method which we use, a resistograph. This is a device which is drilling into the wood, and depending on the resistance of the wood to the drilling power, you will see a resistance. This is shown in a graph, and when there is no resistance in the wood, then the drill will enter the wood much easily, and so you won't have any resistance. And you see in the two top in the two graphs, there is a reduction after 18 centimeters of depth. That means in these, from 18 centimeters, it is from the inside. That means coming from outside, you have a certain thickness which is showing that the wood has been rotten, has been deteriorated somehow, and has lost its resistance. This was not the case in the third one. This was a beam of wood which was just beneath the ceiling and had a very more protected situation from rain, so that there we didn't find any reduction of the resistance. These drillings have been done at 3 different points for each, and I'm just showing one of them. Okay? Thank you very much for your attention. And if you have some questions.